Pop culture often presents a vision of astronauts tending lush, sunlit gardens, but the actual experience of spaceflight nutrition looks more like this, highly engineered and strictly calculated. For a multi-year mission to Mars, aerospace engineers have to work around a rigid biological baseline. An adult human requires about 3,400 calories every day to maintain their health and bone density in that environment. To track the cost of producing those calories, we use a value called phytomass. This is the total mass of plant material required to support one person. In a system where every kilogram of weight counts, phytomass is a critical payload limitation. Initial mathematical models for a 100% plant-based diet, relying on staples like soybeans, wheat, and potatoes, can reach those calorie and protein targets. The cost is roughly 1 kilogram of phytomass per person per day. While supplying bulk energy for survival is mathematically simple, the equation changes entirely when we factor in the long-term health requirements of micronutrients. To understand the true cost of a deep space diet, researchers ran the algorithms again, forcing the system to meet constraints for every essential vitamin and mineral required for a 3-year mission. The mathematical model fails. To naturally meet every nutrient limit using plants alone, the required phytomass balloons to an impossible 10 kilograms per person per day. This creates a terminal payload penalty. Launching a greenhouse large enough to sustain that 10-kilogram requirement makes the spacecraft too heavy to escape Earth's orbit. The vegan space colony concept collapses here. It isn't a failure of ethics, but an infeasible solution in the linear programming of aerospace design. We can trace this system crash to a few specific chemical variables. Specifically, vitamin B12, vitamin D, vitamin K, and fluoride. These micronutrients create leaks in our closed biological loop because they are either entirely absent or present at dangerously low levels in the standard crop selection. One proposed solution is to patch the leak with cargo, shipping thousands of synthetic pharmaceutical pills from Earth to bridge the nutritional gap. But vitamins are fragile. They degrade over multi-year journeys. Since a trip to Mars takes 6 months, the crew has no way to request an emergency resupply if their stock spoils. The mission requires a self-replicating, regenerative source of these molecules that can function without a supply line to Earth. To solve the 10-kilogram phytomass problem, researcher Linda Jones developed a series of models that introduced a new biological variable into the life support system. Her model treats animals as a piece of technology, a biological factory integrated directly into the ship's recycling system. She chose the chicken for this patch due to its high feed efficiency and its ability to recycle inedible plant waste into nutrient-dense food. This also provides a payload advantage. By launching lightweight fertilized eggs instead of live birds, the initial mass required to start the system is nearly zero. The system pivots here, moving from a static botanical loop to a more complex symbiotic biological engine. When we plug the chicken back into the system, we find a balanced model that satisfies the nutritional gaps without crashing the mass budget. The model arrives at a precise nutritional set point, a diet supplemented with exactly 22.5 grams of egg, roughly half an egg a day, and just 3.67 grams of chicken meat. That small daily ration increases the total biomass requirement by only 45 to 70%, yet it permanently resolves the deficiencies in vitamin B12, vitamin A, and vitamin D. This comparison chart shows the difference. The balanced animal integrated model requires only 1.4 kilograms of phytomass, making it the most mass-efficient way to sustain human life. Deep space survival depends on a specific mathematical symbiosis. By acknowledging the chemical limits of plant life, we find that a small fraction of Earth's animal kingdom becomes an engineering requirement for reaching the stars.